Hello everyone. In this lecture, we will discuss the concept of intersymbol interference, and then we will further in the lectures we will describe how equalization can be used to mitigate the effects of intersymbol interference. Let's start the introduction part, in which we have to actually design these signals for a channel which is band limited to some specified bandwidth of W hertz. The point to be looked at is the problem of signal design, because if you understand the theory of communication systems, then the choice with the designer is the design of the input pulse. Input pulse means because in digital communication systems, the information will be represented in terms of ones and zeros. Now, how those ones and zeros will be transmitted through the transmission channel or the communication channel, and how the ones and zeros will be represented in what waveform, right? So that's the point where where we concentrate on while introducing the concept of intersymbol interference. The channel is random in communication systems, and the channel can be modeled as a linear filter having an equivalent low pass frequency response, which is zero outside minus W to W range. That means within minus W to W range, the channel response will be there, but outside this range, the channel response is assumed to be zero. That means the channel is considered as a filter when we have to model the concept of intersymbol interference. Our purpose is to design a signal pulse GT. So that's what I was talking about, that we have to actually design the shape of this pulse GT, which will actually represent ones and zeros. Now, the ones and zeros will be modulated onto this pulse in a linearly modulated signal. Now, Vt is the signal which comes from when these bits are modulated onto this signal pulse. Signal pulse will be a pulse stream, and it will be the superimposition of the delayed versions of the pulses, right? Delayed by capital T time, which is the period of representation of one or zero, right? Then now, when the signal is ideal for when the channel is ideal for mod f less than equal to W, a signal pulse can be designed that allows us to transmit at symbol rates comparable to or exceeding the channel bandwidth. But this is in the case when the channel is ideal, right? But actually, that's not the case in practical situations. The channel is random. That is, when the channel is not ideal, signal transmission at a symbol rate equal to or exceeding W results in intersymbol interference. So if you're trying to send the bit stream at symbol rate or exceeding W, then it results in intersymbol interference amongst a number of adjacent symbols. Now, what exactly is intersymbol interference? Intersymbol interference is the spilling over effect of the previous symbols onto the present symbol, right? Because since the channel is not ideal, so there is a spillover effect of the previous symbols onto the present symbol. So which leads to a kind of interference in the present symbol, in the detection of the present symbol. So you may make a wrong decision corresponding to whether it's a zero or a one. Okay. Now, actually, we have to avoid the intersymbol interference in our communication systems, and we will derive analytically what is the criteria for zero intersymbol interference. Now, to lead to that derivation, we first express the received signal in terms of the transmitted signal, the channel response, Let the function xt be the channel impulse response. All right. Now, if you look at the system model that we will take for deriving the criteria for zero ISI, input data is the is is basically corresponds to ones and zeros. Now this input data will be modulated onto this GT pulse, right? CT is the channel impulse response. ZT is any noise that will be added, additive noise added into the signal, which is from the transmitter side, and while it is going through the channel. Now MT is the receiver filter, which can be a mesh filter for because mesh filter is an ideal filter and it will actually maximize the optimum filter, which will actually maximize the signal to noise ratio. At this point, because what we will get is xt. What is xt? We will represent what xt is. Xt is basically the convolution of the transmit pulse, which is gt, the channel response, which is ct, the receiver filter response, which is mt. So that is what xt is. ht is the convolution of gt and ct. That's what this circle represents. Xt is the convolution of GT, CT, and MT. Right. So at this particular point, we will receive a signal YT. We can express YT in terms of XT, which is the convolution of transmit pulse, channel response, and receive filter. And we will receive a stream of pulses of XT, and we can represent the stream of pulses by this sigma n going from 0 to infinity. And since input bit will be modulated onto this whole composite signal xt, so we can represent yt equal to in xt minus nt plus vt. Vt is actually the noise part. Is that clear? uh, because xt is basically the convolution of transmit pulse, channel, and receive filter. Fine. Okay. Now suppose that the received signal is passed through a filter and the sample and then sampled at a 1 by t samples. The optimum filter from the point of view is the one match filter is signal detection is one matched to the received pulse. That's what is the job of actually match filter. Match filter is a filter in whose response is matched to the input pulse that we have selected. Now we denote the output of the receiving filter. I have already explained how do you denote the output of the receiving filter. That's at this point. Yt is at this point before sampler comes in picture. Now this is a sampler which samples Yt signal at capital T times, periods, right? Okay, so let's look at that part. All right. Now, if yt is sampled at times t equal to kt plus tau, tau 0 is the transmission delay through the channel, where k equal to 0, 1, and so on. So, yt will be sampled at these times kt, where k will determine the timing instants. All right. And sampling instance, and n will represent the number, and n will represent the sample, the particular sample. Now this can be expressed because once it is put in the discrete form, we can represent it by yk, and it says in, because we are only putting the small t value here. We are representing y of small t by kt plus tau 0, and that's what is basically we are representing. And we can express this in terms of this yk equal to sigma n equal to 0 to infinity in x of k minus n, which is actually the convolution of the x with the input signal, plus vk in the discrete form. Of course, vk is the noise part. The sample values can be expressed as, now this is the expression that we get after sampler, right? What we will do is we will separate out the the value corresponding to k equal to c. When we will separate out the value corresponding to k equal to n. So when k is equal to n, in that case, uh, x will become x0. So we will take x0 out, and to the second term we will divide it by x0, right? So what the term we will get? Well, because n is equal to k, because we are dealing with the present instant. What is the present symbol that we are dealing with? So in will become ik plus, because n is equal to k, divided plus 1 over x0, because we have taken x0 out of the bracket, sigma n equal to 0 to infinity, but not for n is not equal to k, because this particular term we have extracted out from this sigma value, in x of k minus n plus vk. Of course, that's the noise part. Now, what is the importance of this manipulation that we have done is that ik, if because x0 is a scaling factor only. Let's come to the next slide. We regard x0 as an arbitrary scalar factor, and if we assume x0 to be unity for convenience, in that case yk becomes this expression. Now this is very important expression. Ik is the present symbol, right, that we will be detecting at the output of the receiver, right, at the receiver side, and this is actually the ISI. ISI means it is this term represents intersymbol interference, the effect of, because yk is the output. What yk contains? Yk contains the present symbol that we are trying to detect and the effect of the previous symbols. All right, and this is basically intersymbol interference. Plus, of course, the noise will be there, right? So ik, the desired information symbol at the kth sampling instant. Okay, and this term sigma n going to 0 and not equal to k, the upper limit is infinity, in x of k minus n. This is basically the intersymbol interference term. Vk is, of course, the additive white Gaussian noise variable at the kth sampling instant. We have to get rid of this term to make intersymbol interference 0. All right. Now, assuming that the band limited channel has ideal frequency response, Cf is equal to 1, which is the frequency domain frequency response of the channel for mod f between minus w to w, within the range, the channel response is, the frequency response is 1, that means constant. Then the pulse x, that means it is kind of ideal response. Then the pulse xt has a spectral characteristic. So this will be the spectral characteristics of the pulse expressed in terms of the x signal. We are interested in determining the spectral properties of the pulse. Actually, that's the important point. Because we have to make this term as 0, we must determine the spectral characteristics of this pulse. Because as I told you, at the hands of designer, if you look at the communication theory a little more deeply, then you will see that at the hands of the designer, the design of the pulse shape is only the design parameter that is in the hands of the designer, which the designer can control. All right. Now we have to look for the spectral properties of the pulse xt that results in no intersymbol interference. Now we know this term, we have obtained this term yk after the sampling of yt signal. We have obtained this term. This is the present symbol that we are trying to detect. This part is the ISI part, and this part is the additive white Gaussian noise part. Now, Nyquist pulse shaping criteria says that which is the Nyquist condition for 0 ISI, the necessary and sufficient condition for xt to satisfy that x of nt at the present instant must be equal to 1, otherwise it will be equal to 0. Right? This is the time domain explanation of the condition. But if you take the Fourier transform of this signal, that will come out to be sigma m going from minus infinity to infinity, because this is in terms of spectra. x of f plus m by t is equal to t. Now let me explain this, the Fourier transform part. It says that the spectra of the x of the pulse when delayed, the spectra, because this is a range of pulses that is coming at the receiver, the range, the index that will determine the number of pulses, the various pulses that are coming to the receiver, that is determined by this index m. Now m is an index. Let's say m is 0, it will be xf. Let's say m is 1, it will be xf plus 1 by t, which is delayed by 1 by t. When m is equal to 2, this will be 2 by t, this will be delayed, further delayed. That means it is a it is a whole range of spectra that we are summing here. The sum of the summation of all the spectra of the xt pulse that is coming at the receiver end should the spectra, the frequency spectra of all those pulses should be a constant t. That means when the various spectra will be superimposed on each other, when the various spectra are received at the receiver, after delayed by 1 by t, multiples of 1 by t, then the summation, the superimposition of those spectra, the whole spectra should lead to a constant spectrum, constant value. That's what is. Now if we are able to design the pulse shape in such a way that when the pulses received at the receiver, when they, because they will be superimposing each other because of the intersymbol interference. But if the spectra, the summation of all the spectra is a constant at the, if we are able to maintain that as a constant, then we will be able to avoid intersymbol interference completely. That is the Nyquist condition for zero ISI. Now let us look at the various cases. The cases now along the y-axis is this spectra, where we have expressed it in terms of n, where n goes from minus infinity to infinity, f of plus n by t. We have replaced m with n, and what it says, it's basically giving the spectrum, the summation of the spectrum. Now, the first case says that if the sampling period is less than 1 over, if the sampling period is less than 1 over 2w, that means the sampling frequency, is greater than 2w, which is the, no, which are the, the channel characteristics, the channel bandwidth. Minus w to w is the spectra of the pulse. Now, if we are sampling at greater than this value, that means the if we are sampling frequency is greater than this value from minus w to w, that means the spectra of the pulses received will be separate from each other. But since at this part, what is the summation of the spectra? Summation of the spectra is not constant, rather not constant value. It is giving 0 here. It is giving 0 here, right? So at this rate, if we choose this rate, there exists no pulse whose spectra replicates and to form a flat spectrum. So ISI is inevitable at this rate. ISI will be present in this case because the condition for Nyquist criteria for zero ISI is that the spectra has to be a flat spectrum. All right. Now this is not a valid case if you want to keep the ISI low. Now the second case is when it is equal to 2W. In that case, the spectra will be, fine, but still there will be ISI present because at the joining of the two spectra, the condition of the zero ISI will not be maintained. The illustrated pulse obviously doesn't satisfy the Nyquist criteria for zero ISI. The only pulse which satisfies the Nyquist criteria is the sync pulse, rectangular spectrum. Now, if we choose the pulse which actually overlap with each other, the spectra at the receiver side will overlap with each other. In that case, the the superimposition values, if you add up the superimposition values, then it will generate a flat spectrum, right? At this rate, when 1 by t is less than 2w, that means the spectra of the other pulses interfere, or I mean overlap with each other. In that case, there exist numerous pulses which satisfy the zero ISI criteria. This has to be understood very properly, because that's the condition for zero ISI, and that is the Nyquist condition for intersymbol interference avoidance. Now, a particular pulse. Now, what should be the type of the pulse that can achieve this goal? A particular type of a particular pulse spectrum for this case that has desirable spectral properties has been widely used in practice, and that is raised cosine spectrum. Now, this is the pulse which is raised cosine pulses, right? The beta value is the roll-off factor, right? So if you design a pulse using this formula, you will be able to get zero ISI. Now, benefit of raised cosine pulse. Well, let's look at the raised cosine pulse first. Then we will come to the benefit part. A popular choice for this case, the raised cosine pulse, beta is the roll-off factor, of course. Now, this is the that's the formula I have given to you, and this is the spectrum, the frequency domain spectral characteristics of the raised cosine pulse. Now, what it says is that uh, for beta equal to 0, it has to be a rectangular pulse, right? So that will not be a good case, because ultimately we have to receive various stream of pulses, and in that case the superimposition, the addition of the superimposed values, if when they are added, they should result into a flat spectrum. Now, this is one pulse only, which is rectangular pulse, but due to the channel impairments, we will not be able to get, if we choose a value beta equal to 0, then we may not get a very um, particular value of the particular this rectangular shape. Now, in that case, if you look at the spectra very carefully, when you increase the value of beta, when you make beta equal to 0.5, the it will not suddenly, the raised cosine pulse will not suddenly come to zero value. It will roll off, and it will extend beyond its bandwidth. This is for one pulse. The another pulse will also come like this and will overlap with other pulses. So once the pulses are being overlapped, in that case the summation of the spectra of these pulses will lead to a flat spectrum when the superimposed values will be added with each other. And if you further increase the value of beta, what will happen? It will further extend beyond the bandwidth, right? So in that case, you get a better extension of the spectra of all the pulses, and that will basically lead to the Nyquist condition to be fulfilled in a more appropriate way. So increasing the values of beta will actually lead to the fulfillment of the Nyquist criteria more appropriately. ISI will be reduced in a great way. That means increasing beta, more ISI going to 0. But there is a drawback here, that it will also take more bandwidth, right? So in that case, you will have to make a trade-off between the ISI and the bandwidth utilization. Correct. Now, this is the time domain characteristics of the raised cosine pulse. For various values of beta, we have plotted. All right. Now if you look at the various characteristics of the various advantages of the raised cosine pulse, you will see that the benefit of raised cosine pulse, it decays as 1 by t cube. If you see in the formula, you will if you take the time domain version of this formula, you will see that it decays as 1 by t cube. So any sampling offset results in finite ISI. If you have any offset, because this pulse decays at 1 by t cube. So if even if there is a sampling offset, meaning by when you are sampling at capital T time, no, if that instant is offset by some value, even then in that case the raised cosine pulse will decay very quickly. Now with larger beta, the pulse decays faster, right? But the bandwidth utilization is poor because uh, it extends beyond the bandwidth available. So I mean that you will have to your bandwidth utilization will be poorer if for larger values of beta. Now it is possible to design practical filters that implement the raised cosine pulse. Okay, so with raised cosine pulses, we will be able to ideally saying that we will be able to achieve zero ISI. But the point is that in practical scenarios, this is the condition when the channel is not time varying. But in actual circumstances, channel varies with time. Channel is not constant. Channel is varying randomly. In that case, uh, the zero ISI, even if you have designed a pulse for the particular channel condition, if you have designed a pulse, but since channel is time varying, so you will have to adaptively design the pulse shape to bring the ISI to zero. But this is a very impractical situation where every time when the channel is varying with time, you will have to adaptively design a pulse, because that is not possible practically to design the pulse adaptively as your channel conditions are varying. Now, what is the solution in that case? In that case, we will have to we will have to do something at the receiver side. We will have to design a block at the receiver side which will be able to cater to the effects of intersymbol interference. And that particular block which we will design, basically it will be a filter, and that filter will be called as that process of um, equalizing the effect of ISI when it is not able to hold the Nyquist condition for zero ISI. In that case, that filter part will try to reduce the intersymbol interference practically as far as possible. Now that process of that process of removing the ISI through that filter, and that filter is known as an equalizer, and that process is known as equalization. We will study the effects of equalization, various conditions under which the equalizer can be designed, and how we will be able to use the equalizers for reducing the ISI in the practical scenario. I finish my lecture here. Thank you.